Section 4.2 here is going to look at some applications with linear functions, and some of it's easy and some of it at the end is pretty hard. So let's take a look. So we need a line here. What they've told us is that we've got an initial population. In 2009 we've got it to be 8,100. So we need a function. So we need and this function is linear, it's growing linearly. So we know this. If this is the initial population, this is B. B is 6,200. And now we know that it's grown to 8,100. Well, what could we do? We can find the slope. So this is 0. 6,200 is 1 point. And this is, so it's 5 years later, we have a population of 8,100. I have 2 points here, and this one point just happens to be the y-intercept. So we can find that slope, and it turns out to be 3,800. And we had that initial, so there is the equation. Now, it wants the population in 2013. Well, that's 9 years from our initial. So 2004 is our initial year. So this is 9 years later. So we are plugging in 9. Crunching that down, we get 9,600 people. Now, they want to know what happens, when do we think we will have a population of 15,000? Well, this is an equation about population, so the y is standing for population. This just goes in here, and we solve it for t. Okay. This one's a little easier here. So we are finding a cost function. It's a linear situation because I have one fixed cost, and then it's 25 cents per donut. So I'll talk you through this if you don't remember. So we have the fixed part. It's not changing. It's just 25,000. It's 25 cents per. So that's a slope. So here's the cost function. This is the answer to A. Now we want to find and interpret the y-intercept. Well, the y-intercept is that initial cost. So in terms of this story, our initial cost, or our intercept, is about what happens when there's no x, when x is 0. I keep forgetting so each donut. Okay, x is producing each donut. So if we're producing 0 donuts, our upfront costs are $25,000. So that's what story is. It's kind of obvious there. Okay, this is a little out of order. This is more like the one that we just saw. So I have 2 points. Now the second point is 4. So 2008 is the initial. So I'm calling that year 0. 2012 is 4 years later. So I'm going to call this 0 and 4. Like it's in relationship to the start of this here. And so 36,800 is the second. Okay, well we know B, because if this is the initial population, then that's B. That's the initial. That's when x is 0, and if it's x is years, then that's our initial population. Okay, now we need the slope. So we're going to do 36,800 minus 28,200. Just doing the y's, just the basic slope formula. Now 4 minus 0 on the bottom is just 4. So let me crunch this on my calculator. So okay, I get a slope of 2150. So let's build our equation. So I'm going to call it population. You can just leave it as y, whatever you want to do. But this is my slope, and my initial was 28,200. So they want to predict the population in the year 2014. Well, that's 6 years after this. So we're evaluating this when it's 6. So P of 6. So if I crunch that right, when 6 years from now, we're expecting a population of about 41,000. Okay, when is the population going to reach 54,000? That just means we want this population and we want our y to equal 54,000. So, sorry, got something on my keypad here. Okay, so we're just doing a good old school solve this for x. So I'm going to do this all in one shot. So I'm subtracting the 28,200, then dividing by 2,150, and x is going to be 12. So we think that's going to happen 12 years later. Now, if it actually wants the year here, maybe I didn't catch this on the earlier one. If we started in 2008, so in the year 2020, well, it'd be 12 years after that initial one. Okay, now these next few, I can't remember how many there are, but these get a little bit crazy. I've actually never seen problems quite like this before. Here's what they're saying. We are going in two different directions. I've got Anna walking east. She's going 4 miles an hour. Now that's a rate. And we've got Samuel or Emmanuel walking south at 3 miles an hour. So we could think of this. We don't know how many hours each of them are going. So you could do some things with signs here to make this a little more clever. But we're just going to say here's our two lines. We've got one going at a rate at 4 per some amount of time. The other person is going 3 for some amount of time. Now, what it's saying, if you even caught what this story is saying, at some distance between them, the radio that they're each holding on to is going to cut out. And so when this distance is 2 miles, then the radio cuts out. So look what we're going to do here. Again, this is pretty clever. Never seen a problem quite like this before. I have the two equations, and we've made a triangle. So I've got this is, I can't remember which is which. I think I would call it x. I think that's the right people. Okay, so these two sides of the triangle are like 3 I don't know and 4 I don't know. Well, we could find the hypotenuse by using the Pythagorean theorem. So this is the one side. It's 4 times I don't know. 3 times I don't know is the going down. We crunch this, combine like terms. Now, we come up with this equation. Remember, the Pythagorean, that hypotenuse is squared, so we had to square root it. So this looks pretty crazy, but so we're not going to want a negative distance. So when we square root this, we're going to have this distance side, this hypotenuse, is going to be 5 times t. Now they're being real clever with some notation, but this is all we need, 5t. Okay, now when is that distance going to be 2 miles? Because that's when their radios are going to cut out. So if we knew this, the distance equals 5t, well, when is it going to be 2? What is the time that's going to make this 2? We'll divide both sides by 5, and t is going to be 2/5 or 0.4. So in 0.4 hours, if they're walking in these distances, one south, one east, in 0.4 hours, they'll be 2 miles apart, and that'll be the end of their radio signal. Again, I've never quite seen one like that. It's pretty clever. And this one is even trickier. So let me kind of walk you through this story here. So we've got this town, and 20 miles east of it is this other town. So if we put this on a grid here, I've got this second town here. Sorry, what happened to my pen? There we go. The second town is 20 miles east. So I'm going to put this on a coordinate grid here, and I've got the point 20, 0. Now, I've got another town. Let's see. Yeah, I've got another town here at 30, 10. Let me just read. Okay, so this picture is everything that we've got. There is some junction road that is perfectly perpendicular, and it's right here, creating this triangle. Now, what we want to do is find the distance. What are we looking for? How far is the road junction from Westboro? So we're looking for this. We want to know from Westboro to this junction point right at the end. So we're basically looking for that side of the triangle. Now, in order to do this, we're going to need some more information. If you have two sides of a triangle, we'd be in good shape and we could just use the Pythagorean theorem, but we don't. We only have the one. And so they do something very clever here. Because we knew this town of Agratown or whatever is located here, what we could do is make the equation for this line. So, or at least we could find the slope. So between 0, 0 and 30, 10, we could find the slope of the line that's between them. And when they crunch that, yeah, so it turns out, I just want to make sure we're using the right thing. So it turns out to be 1/3. So in our y-intercept here for this line is 0 because we're going through the origin. So they have made an equation for this line from Westboro to Agratown. Does that make sense? They just took the slope. That's all they did. And you're thinking, well, why do they need that? Well, let me show you. It's pretty clever. Now, we know that this road is perpendicular. So let's find a line for this guy right here. Let's find an equation for this line. And the way we can do that is because we know that that line would be perpendicular to the other. So if the one had a slope of 3, the slope for this line being perpendicular will be, oh, I'm sorry, if it had a slope of 1/3, is that what it was? Yeah. If it had a slope of 1/3, the slope for this one is going to be upside down and have the opposite sign. So the slope for this one is going to be -3. Well, okay, well I have this, but I don't have the y-intercept for this new line. Well, all we have to do is use a point, and we have one. We know that Eastboro is a point on that line, so I can put in 20 for x and 0 for y. Solving that for b, just like we were doing in our earlier sections, I have an equation now for this line here, right there. And I have an equation for this line right here. Now, what good is that going to do us? Well, remember systems of linear equations. This junction point right there is where these two lines intersect. And so I'm going to set the two lines equal to each other. It's really the same thing. You're doing the system of linear equation thing. You've got one line is this. You've got another line was 1/3 x. But it's substitution. If I know y equals this, I could just sub it into the other. And so that just so happens to be, you could just set the two equal to each other. The point of intersection is where these two lines hit each other. So where if they're both equal to y, I can set them both equal to each other. Now, if we solve that for x, I come out with 6. Well, that's an x value. If x is 6, let's plug it back into either of our equations to find the value of y. So I'm going to go to this guy. So if x is 6, 1/3 times 6, y is 2. So these intersect at the point 6, 2. So back to our picture. This is the point 6, 2, with some very clever use of the knowledge of lines. Okay, well, so what? What good does that do us? Well, what we wanted was the distance from Westboro to that junction road. And we have 2 points. Well, when you have 2 points, you can just use the distance formula, which is really derived from the Pythagorean theorem. So I've got my 2 points. Wait, why is it 18? Hold on. Yeah, I guess I've used the wrong formula to plug it back into. So we found x was 6. I'm not sure what I'm doing here. But if you plug it in here, this equation, you get 18. So I'd have to figure out what I did wrong there. But so we get the point 6, 18 for that junction point. So plugging that in to our distance formula, we crunch it down, and we get the distance between those 2 points. Again, that should have been an 18. The distance from those 2 points is about 18 and well, almost 19. Okay, now let me see what we got here. So let's do it again. Now we got the same idea. So I'm going to draw my picture here. I'm going to set this up on an axis. And we've got this town is 60 miles east. So I'm going to set this up here. This is the origin, of course. And then, oh, hold on. I've got my wrong picture here. So this is not right. So this is 60 miles east and 12 north is this Ashburn town here. So 60 miles east would be x. 12 miles north would be the y. So I've got this line going here. Okay, now they say there's this town directly east. This is the one I should have been going to. So directly east, we put it at 22, 0. And although my picture isn't working quite right, they're going to tell us this road here, the junctions, the two of them, is perpendicular. All right, now we have exactly the same problem that we had before. We're going to find the equation for this line, and then we're going to find the equation for this one. It'll allow us to find the intersection point. So what do we have here? So we have, I'm doing this line here. We'll call it the Ashburn Road. So I know that my y-intercept is 0 because we literally hit right there at 0. So I know my y-intercept. What I need is the slope. So 12 minus 0 over 60 minus 0. So this is just y2 minus y1, x2 minus x1. So this is going to be 12 over 60, which is going to turn into be 1/5. So this first road is 1/5 x. Now the junction road to Timpson is this. We know that it's perpendicular, so its slope is going to be 1/5 turned upside down with the opposite sign. Now the problem is I don't have the y-intercept, but I know a point on the road. It's this one. So all I have to do, oops, I did that wrong again. Okay, so I put in an x of 22, I get a y of 0, so I can solve this. Make sure I don't screw it up. So 110, so negative 110. So b is going to turn out to be 110. So I now have the full equation for this line right here. So I have the two lines. I have this line, I have this line. Let's set them equal to each other so we can find that intersection point. I get 1/5 x is negative 5x plus 110. Okay, let's get all the x's back together. So I've got 5x plus 1/5 x equals 110. I'm going to turn this right here over to 25 into 5 so I can put these together. So I've got 26 over 5x equals 110. Now you really are keep, change, flip, but you can just think of it as what you're really doing is multiplying both sides by the reciprocal. So what do I get here? Okay, so x is going to turn out to be 21.15. I'm surprised these numbers are so bad. I don't think anything's wrong, but this is a pretty bad number for this problem. But so, okay, so our x value is 21.15. Now to find our y, we're going to plug this back into our equation. So let's use this one. I'm using the Timpsonville line. And I get 4.23. I think everything's right, but I'm a little surprised with all these numbers. So 21.15 and 4.23. Okay, now that's the point right there of the junction. I've got it. Now there's only one thing left to do, which is the distance formula. So that's x2. So we want the distance between these two guys right here. So that's this x minus this x. Well, that's just 21.15 squared. And then it's plus this y minus 0, which is still just going to be 4.23 squared. Okay, I'm not really excited about crunching this, but I'll do it anyway. I was going to let it go, but okay, crunched all this down. I get 21.56. Okay, so this road here, the length of this road is 21.56 miles. Yeah, miles. Okay, first of all, so we've got another application here. I have seen this one sometimes. We want to see where which of these two companies is the best financially for us after some point in time. So first of all, we need two equations. So the first company charges an upfront fee of 20. So that's going to be a y-intercept. It's just going to be 20. And then we've got a changing amount of money of 59 cents per mile. So that is going to be a slope. So here's the first one. Now remember, it was cents, so 59 cents per mile for some distance. The other company has this information, upfront fee of 16.63 per mile. Now what we want to know, what did we want to know? Okay, so the first company, the Keep On Trucking, has a larger upfront fee, but because it's less per mile, at some point it's going to be the better way to go. So what we're trying to find is, when does that become the better choice? And the secret to this is, let's just see where the two of them intersect each other. So we're just simply doing, it's really the substitution method, or you could think of it as just setting those two equal to each other. It's the same thing. We solve for this and we get d equals 100. So these two lines intersect at 100. Now, the first company was cheaper all the way up until there because of the lower upfront cost. But now when we reach this point, they've now are exactly even. You could have chosen either company and you'd be paying the same amount. Okay, well, past that point, because of the lower rate each time, the lower mileage rate, the Keep On Trucking Incorporated would then become cheaper. So one more time, we've got these two equations, which were kind of easy to build just from what they gave us. The, I don't know what it was called, the M company, Move It Your Way, is cheaper because of the lower upfront charge. Now, we found where they hit each other, which would mean this is where they're worth exactly the same amount. They're both costing us the same. But because after that point, because this is a cheaper per mile rate, this will make the Keep On Trucking the cheaper option. Okay, so some pretty unique linear applications there. Some of those are pretty challenging. If I gave you one on an exam, I would keep it exactly like one of these versions. I wouldn't stray too far from that. So hopefully these made some sense.